The last little bit with chapter 17, I think it is, with respect to primarily vitamin B12, since that's something that's new that we haven't seen before, and it has really interesting chemistry and it's very important. And then we'll pick up with chapter 18. Okay. And so, the way that we got on this is the fact that vitamin B12 is used to make coenzyme B12, which is used in this instance here in this mutase, which will take methylmalonyl-CoA into succinyl-CoA. Okay, so the interesting thing about this is that we can actually utilize odd-numbered carbon-containing fatty acids as an energy source, because we get down to 3, which is propanyl-CoA, and it ultimately makes something that goes directly into the citric acid cycle. So this actually explains how there are diets that consist primarily on food groups that are higher in the odd number containing fatty acids. Okay, so it is possible. It may not be very flavorful, but it's possible. So vitamin B12 reactions, typically what these are involved in is that they can transfer alkyl groups, or even things that are substituted alkyl groups, with the hydrogen that's vicinal. What does vicinal mean? Do you remember from organic chemistry? Next door, same vicinity, right? Versus geminal meant it was hanging off the same parent atom. Vicinal means it's next door. But which doesn't sound like a big deal, except for the fact that what's remarkable about it is that hydrogen never leaves. You cannot get it to exchange with water or alcohol or anything like that. It stays within the enzyme complex. And so the way that this works has to do with the mechanism that B12 works at, okay? And that's one of the reasons why this is amazing, considering the fact that there are so many free hydrogens since we are water-based, okay? And so that's one of the reasons why, if you remember back to organic chemistry, how alcohols, that hydrogen many times can disappear when you use deuterated water, because hydrogens from alcohols and amines in particular, and carboxylic acids, often do what's called solvent exchange. This one can't do solvent exchange. So this is vitamin B12. All right. And one of the interesting things about vitamin B12 is it actually utilizes cobalt. Okay? And so cobalt is a trace element that we do need. We don't need very much of it, but we do need some some cobalt in order for this to be able to make cobalamin and vitamin B12. It has a ring that's very similar to what we saw with heme. But with heme, what was the metal ion that was used? It was iron. Okay, but this one's called a corrin ring, but it's very similar in many ways to the porphyrin ring. And what happens is this complex is formed by cleaving off the triphosphates from ATP. Normally, we either cleave off a single phosphate or the diphosphate, but not the triphosphate, right? So normally we make either ADP or AMP, but not just A. And there's only 2 known reactions that actually occurs this way. And the other one is going to be the formation of SAM, which is S-adenosylmethionine. It's also called Adomet, by the way. And that's in chapter 18. So this is what it looks like overall. We have the attached deoxyadenosine right here. We have the corrin ring system, and then we have what's going to be this instance right there. This is a ribonucleotide, but they're just showing you as one that's being an analog to show you what it looks like. Okay. What makes this special also is that the reaction between this deoxy A and the cobalt is very weak. And whenever it breaks, it doesn't break heterolytically. Remember, that was a term where electrons go to both, and both electrons in a bond go towards one parent atom. Here it's homolytically, to where we're going to actually form a radical, but that free radical doesn't ever exist in free species, so it's held in place. And so let's look at how that occurs. Okay.
Lowercase d, capital A, that's deoxyadenosine?
Mm-hmm. Oh, this thing keeps going backwards instead of frontwards. Okay, so this is just a kind of a blow up showing the important parts. So we've gotten rid of all of the core and ring. We got rid of the other dinucleotide, ribonucleotide down here, to where now we just have the cobalamin and the ATP. So this is the cobalt. And what it does is it comes in and attacks the C here and pops off the triphosphate. So now we have this weakly bound deoxyadenine, see, because that's why it's DNA, otherwise it'd be RNA. But it's the base, the ribonucleotide, not the phosphates that's actually added on. This is the reaction scheme for this, and I'm going to just take you through it and walk you through it. So this is what coenzyme B12 looks like simplistically. And what happens is within this enzyme complex is this is really weak, and it goes through homolytic cleavage to where one electron goes up to the DA, is what I'm going to call it, and one of them is going to stay with the cobalt, because cobalt starts off as a 3+ charge, but now it's a 2+, so that's why you got one of the electrons. Then comes in the substrate, whatever it is that you're wanting to swap the alkyl group with the hydrogen. Since this isn't completely happy and is held within the binding site of the enzyme, what it does is it takes the hydrogen off of that substrate, the one that you're wanting to move, but it only takes one of the electrons with it. So now we have the substrate's a radical, but the DA is neutral. So since we have a free radical here, of course free radicals can move around. All that happens is the X and the free radical swap places. And then this is where the cobalt comes into play. And they don't actually show it here, but the cobalt 2+, I'm sorry, I misspoke. This is where the DA and the cobalt ultimately came into play. But the DA then will swap and move the hydrogen back over to where we have what we saw in step 1, and with the DA free radical, and then the cobalt will come in and give up the 1 electron in order to be able to bind the DA once again. So just to reiterate, this is a weak bond that splits heterolytically, so that way the hydrogen off the substrate can take 1 electron with it to form a methyl group. And then the other electron is staying with the cobalt. You swap places with the free radical, we get the hydrogen back, and then the cobalt will go and reform the bond within vitamin B12. So it's not this, the free radicals never leave, so you don't have, assuming it's healthy, that you don't have to worry about any type of free radical damage that's done many times that we've seen in the past. I just also usually try to pick out something that's, medically related. Just to point out that the plants and animals don't synthesize vitamin B12. So this is something that we have to get in very, very small amounts. And so we get it from microorganisms, certain like probiotics that help us get our vitamin B12. There are certain diseases where people, and maybe you've been tested, someone's tested and has some of the vitamin B diseases. That's where your body has problems absorbing the B vitamins. And so one way to, this is just one instance where they have the failure to absorb from your normal flora, bacterial flora of your gut, or the ingestion of meat. And so you get what's called pernicious anemia. And so with pernicious anemia, since you're not getting enough vitamin B12, you aren't going to make enough of the cofactor B12, and you make what's called insufficient intrinsic factor. Okay, and then you get reduced number of erythrocytes. It causes reduced hemoglobin since you don't have enough blood around there, and eventually you get severe progressive impairment of the central nervous system. Okay, so this is one of the reasons why make sure that if you aren't a meat eater, like I don't eat much meat, that you want to take some type of vitamin supplement that has this in it, or you can take probiotics or something like that to make sure that you are getting enough of the bacteria and things that your body utilizes to make vitamin B12, because we can't make it ourselves, and neither can plants. Okay.
So that would be the failure to absorb is due to like the cilia?
Oh, I'm sorry. The failure to absorb with respect to that disease with insufficient intrinsic factor.
So when it's going through your small intestine?
Right. Mm-hmm.
So is it because like the cilia is not picking it up? Like the cilia level here?
Right. Yeah. I don't know in this specific instance here if it's due to the cilia or if it's due to some other portion intestinal disorder, or if just people don't even have enough, or sometimes that's one of the bad things if you take too many antibiotics too, right? You can kill off the good, quote unquote, good bacteria. Then you can start developing some of these anemias based off of this as well. Okay, and you usually are sluggish. You have problems with fatigue because your oxygen levels can ultimately get low as well, and bad things can happen if you don't.
Yeah. Like in pernicious anemia, would you see like lower levels of like liver enzymes or anything, or would it just be
I think
low
that.
levels of vitamin B12?
Well, no, I mean for pernicious anemia, one of the hallmarks would also then be a decrease in iron, right? You're not having iron in your hemoglobin. Your hemoglobin count would be down for anemia. Mm-hmm. Okay.